Hello. Today we will be talking about Topic 2, Section 9, titled Further Modeling. So the first thing we should talk about is exponential growth and decay. So hopefully you recognize that this would be the growth and this is decay over time. Notice the equations are very similar. They both use the number e. And if you remember your formula for exponential growth and decay, you start with your initial amount and then you multiply by e to the plus or minus x, right? Positive if it's growth, negative if it's decay. Okay, and actually, what did I forget? I forgot, let's see, Cognity uses lambda t. Okay, so where lambda would be your the constant. Okay, so like your percentage, what your growth and decay amount would be. Let's see, and then it equals your future amount. All right, it's a lot easier to do with examples, so let's start there. So let's start with example 1. So after 1,000 years, a sample has decayed to 64.7% of its original amount. So find the half-life of the radium. So first we need to think about our equation. So if we start with some initial amount, okay, so we'll call that A sub 0. So that's 0 would be what it starts with. Okay, we multiply by E, and since it's a decaying problem, we know that is going to be a negative lambda. Okay, and let's see, and it's after 1,000 years, so we're going to multiply by t, which would be 1,000. And we want this much left over. So if we started with this amount, well, we want 0.647 of that amount, okay, because that's what we're going to end up with, okay? So then we can work on solving for lambda, which is our decaying constant. All right, so we can divide out the initial amount, so we get 0.647 equals negative 1,000 lambda. Then we can do, essentially, lambda would be the natural log of 0.647 all over negative 1,000. Yes, and this should get you approximately 0.000435. And now that we know what the decay constant is, we can figure out what the half-life would be. So what I would do is I would plug that into my calculator. So I would say store that. And then when you solve for the half-life, we can just plug that variable in instead of trying to write out that whole shindig, right? You don't want to round anywhere in the beginning. Okay, so we know what lambda is. Now we want to find the half-life. Okay, so the half-life is we start out with some initial amount, okay, and we want 50%, so 0.5 of that original amount, and we don't know what t is. So now we're just solving for t. The initial amounts are going to cancel out, and then we know what lambda is. That's stored in our calculator. So now we can just work this out. So time should simplify to the natural log of 0.5 over negative lambda. So let's put that into our calculator. So what I mean by that, let's see, we're going to do the natural log of 0.647, I hadn't done this yet, divided by negative 1,000. To store that, I'm going to hit the STO arrow button. So it takes my answer and then it's going to store it. And then I'm going to do alpha, pick a variable. Okay, I'm going to pick x, so I'm going to do alpha store. So x is now my lambda, okay, in here. So now to solve this next part, we do the natural log of 0.5. And then here it was my last answer, so I could just divide by negative that answer or use my alpha, my negative x. And so now I get 1591.94. 1591.94. So the half-life would be 1,592 years. Ooh, did I put the wrong? How did I? That's not what Cognity is saying. Oh, I bet you Cognity rounded. Ooh, they did. They rounded that 0.435. Don't do what they did. Let's store that. Okay? Okay, so Cognity used rounded answer. So no, don't do that. Okay? And what is this? I totally forgot about unveiling that. Okay, well that was the equation. So instead of showing you, I guess I just wrote it all out. All right, but that's how you want to set up your growth and decay. So it's just knowing how to plug it in. Okay, so now let's model a exponential problem. So here we have this equation. Now here. Okay, so we know that it's going to be some amount equals the initial amount times e to the negative lambda t, because it's decay, it's going down. Well, right here, that's the initial amount, right, when there's 0 time that has passed. So now we've got a start. And let's see, we know what this means is here's our time, and that's our output. So 25 would go here, and then we have e to the negative lambda times that's 1611.9702. And then here you can just solve for lambda. Okay, which I believe if you work this out, it's the natural log of 1/2 all over negative 1611.9702. Okay, and that means you should get 0.00043. Okay, and that is our lambda, so then our formula should be 50 times e to the negative 0.00043 time. Let's see, did we get it right? Sweet, we did. Perfect. All right, so example 3. So now instead of giving it a graph, we're given basically 2 points, right? We know after a certain number of years, it weighs a certain amount. So using our formula, all right, we can plug each of these in and make 2 equations. So now we've got our 2 equations, and usually when we have 2 equations and 2 variables, we substitute or eliminate, okay? Well, we can also do more than that, okay? We can also divide. So on this one, we can actually kind of set up a ratio. The left side over this side is going to be equal to this divided by that. That ratio should be the same. So 10 over 8 is going to equal the first term times e to the negative lambda times, well, I'm going to write this nicer, negative 541 lambda all over initial amount, e negative 838 lambda. So we can set up a proportion. Okay, so now we can just solve, right? We know these initial amounts are going to cancel. So now we get 5 over 4, right? I just simplified that. And then here, they both have an e, so combine those by subtracting. Negative 541 minus negative 838 should get us 297 lambda. Move it over. Let's see. You solve this. You get the natural log of 5 over 4 equals 297 lambda. So do the natural log of 5/4 all over 297. And you should get 0.007513. Okay. So now we've got our lambda. And now we can plug it in to one of our answers, or I'm sorry, one of our original equations, and solve for our initial amount. So now let's solve for this. Okay, so we're basically our initial amount, right? That's what we're looking for. The initial amount would just be 10 divided by e to the negative lambda, which we just solved for, times 541. So let's plug that into our calculator, just to make sure we know how to. So the natural log of 5 over 4, make sure you end the parentheses, divided by 297. That answer. Again, we can store it as x if we would like. And then here, we're going to do 10 divided by, I'm going to put parentheses just to make sure, have our e to the negative 541 times rx. Okay, so here we get our initial amount is 15.015. I guess that was more rounded, so I'll do it like this. All right, so let's see how we did. There you go, to the nearest kilogram. I always double check those rounding. All right, so that one said 15 rounded. Okay, so now let's talk about log models, so logarithmic models. So they're in the form a plus b times the natural log of x. Natural log is just more useful. You see that more in the world than you would just regular log. Okay, so we use natural logs. So here we've got an example of a log function. Notice how it has more of a curve to it. Here we've got it frozen to box office performance. All right, so here we have our weeks after the release date and how much money they made. Okay, so here it's graphed. Now, how do we make a log equation? Well, there's two ways. We can do it algebraically or the calculator method. So the algebra method would be, I'd pick this point to the left and this point to the right, and I would plug those values into the a plus b times the natural log of x. Okay, so I'd make two equations, and then I would use substitution, elimination, and solve. Okay, so substitute in points and solve for missing variables. All right. The calculator method would be where you would actually plug all of this into your calculator. Okay, so plug it into your lists, list 1, list 2, and then you can use your log function. Let me see. If you had already put it in your stat list, remember, stat, edit, put them in there, and then when you're done, you would go to stat calc, and you would go down to until you see the natural log. Well, sorry, you would go to the natural log regression. Sorry, I thought it had the equation next to it. I guess thinking of linear regression. Sorry. So ln is natural log regression. Then you just make sure you pick your lists, and then you can store your equation too if you'd like. And that's where we get this answer. So we're going to be very, very close with our two equations. All right, the calculator method is going to be, of course, more precise because it can kind of take into consideration all the points, and doing it by hand is a little bit trickier. Okay, so let's look at a sinusoidal model. I don't know if I'm pronouncing that right, but a trig model, essentially. All right, notice that this is a sine function. The equation would be right here. So here we've got our points, and here we've got it graphed on a scatter plot. And we could plug in some points and try to do that algebraically, but that's tough because notice we've got 4 different variables there, and two of them are inside the function. It can just be messy. Okay, so we can kind of logic it out too algebraically. Okay, so what I mean by that is the highest point is 12 and the lowest is 10. So in a trig function, you want to look for the amplitude. So the amplitude would be half of the total height. So if the height of the whole function is only 2, then the amplitude would be 1. All right, we also know that the vertical shift, so the amplitude would be our A. Okay, so let's see, what else could tell? Oh, D is your vertical shift. So here we got the amplitude to be 2. D is the vertical shift. So that is the average of kind of like the middle of your graph. Okay, the average of the highest and the lowest. So the average of 12 and 10 is 11. So the vertical shift is 11. All right, so now we need to find what, C and D? I mean, B and C. For B, we're looking for kind of the period. I was trying to think of the shift. I couldn't think of the word. Okay, so B would be the period. So here we know that the minimum is at 10. And then here we can assume that the minimum would be between 20 and 22 years, so around 21. Okay, and then so that is a change of 11 years, because right, year 21 to 10. So that period is going to be 2 pi divided by that distance. Okay, because it's supposed to jump every 2 pi. All right, or repeat every 2 pi. All right, and so now, let's see. Okay, so for C, that would be the horizontal shift. So that's going left or right. So, how Cogni did it is that they said there was a relationship between, well, since the horizontal shift, the vertical shift was at y equals 11. All right. Our equation's not going to quite be at 2. It's probably going to be a little bit under. Yeah, so they basically just estimated. Okay, and that's what you can kind of do too. Algebraically, that seems to make the most sense, right? Plugging it into your calculator, that was our last number to plug in. It'll be okay. All right, so that became, what, 1.5 is what they used? Okay. So we get this equation. Of course, when we plug these points into our calculator and we use our trig function, we get this. All right. And here you can see both the equations are really good. okay? The calculator one is usually better, of course, but doing it algebraically can still get you that close enough. And just so you know, on your calculator, the sinusoidal model can be found on the StatCalc as sinreg, okay? So the regression line of a trig, of a sine function. All right, so for this one, I thought I would just walk you through what they did in Cognity, okay? So the first thing you want to do is draw a scatter plot. So put that into your calculator as your two lists in your stat function, okay? And then you should get this as a scatter plot. Okay, now we're going to use those three population dates, so 1815, 1830, and 1845. So we plug them into our general form, which is this equation right here. We get these three equations, okay? Pretty gross. I don't like looking at the fraction, so why don't we take that denominator and multiply it by the other side? Well, then you get L equals this big number times that. Well, so what you want to do is then all of these become L equals. So that means they all equal each other. So then that's how they got these two equations. They multiplied this times the other side and got here. They multiplied 247, 113 times this, times this bottom one, and put it right here. So the top one equaled the middle one equals the bottom one. Okay, so that's how they got their two equations. So great, now we've got two equations and two variables, but this is not very pretty. So they distributed, to take the first equation, they distributed the 3,600,000 whatever here, and then distributed the 4 million over here, and then got the C's together, moved that over to the other side, the 3 million to the other side, pulled out the C, and now got C by itself. And they did it for the second equation, right? Pretty gross. So you could do one of two things. You could either set them equal and then solve. I believe that's what they did. They set them equal, and then they got, they just rearranged the proportion, okay? And then they graphed this left-hand side and the right-hand side. So the left-hand side was this pink line, this right-hand side is these blue lines, and the intersection is right there. Okay, we want time to be positive. Okay. Well, not time, that's not what we were solving for. It just wouldn't make sense if k was 0, because in my equation, if k is 0, well, then we just have a straight line, right? We lose all of our curve. So that's why we need to use this one. Okay. Let's see, there's other ways you could have approached this too, you know, using your equation solver. I'm not sure, but there's only one point, so I imagine it would work. But I liked how Cognity did it, okay? Because it can get a little weird, but I liked how they worked it out. If it doesn't make sense, just let me know. I can happily go through it again. Let's see. Yes, then we solved for k, we plug that in, then we get that value c, and from there we can get L. So it's just a matter of working it back in, because once we get k, we can plug it into one of these equations, one of these equations and solve for c. Once we get k and c, we can plug it in one of these and get L. All right, so then using the logistic regression option on your calculator, all right, to do that on the calculator, we would use that stat function. So the logistic, yeah, it would be the logistic one. Where did it go? All right. And let's see. Commenting on the difference between the two models. Where's my... Okay, so here we can see both models represented. Yeah, the only really difference is the pink one's a little bit higher, and that means it predicts a higher carrying capacity. Okay, whereas the one we did by hand kind of predicts it on the lower end because it's below it. All right, so if we are 2020, okay. According to the worldometer data, the population at the time of writing this is this. Does that change the model? Well, let's look at our model. So if we add that point to the graph, bam, look where it is now. Yes, I would say that does change the model. And let's see, increase in population for some time from now with stabilization a lot higher than where we predicted. So this will be what, over, I can't read that, 12 million? Whereas over here it was only around 7. It was a little over 7. So that's a big difference. Okay, so yeah, I would say that point really changes our predictions. Okay. All right, so hopefully it makes sense with logistic models. Really, it's just using those stat functions, which I believe you guys are all familiar with. It's just using the different regression lines. Okay. Let me know if you have any questions.